So yesterday we talked about AC and DC. I gave you an introduction to the course, and I mentioned a packet that was on Blackboard that I wanted you to go look at to see the power distribution system as well as some other concepts that we talked about. So here is that packet, and you can see we talked about the reason for AC and DC, and we mentioned the fact that if I transmit or if I move power in AC form, it's much more efficient than moving power using DC. And so what you see here is a picture of a power distribution system. Here we have a dam, and the water falls over and turns some turbines. We talked about a rotating machine and the generator, which I'll show you here in just a second. So you got to have something that will cause the turbine's blade to spin the coil and the magnetic field that we discussed yesterday. But what I want to show you here is we talked about a device called a transformer, and you can see here that what we do is we take the energy from the rotating turbine, which it starts here as potential energy. The water falls over the dam, spins the blades, and that potential is turned into kinetic energy, and then the kinetic energy, the rotating shaft, the kinetic energy from the rotating shaft is converted to electrical energy. But the point I want to show here is the voltage is stepped up. It actually stepped up a couple times. So we run through a couple step-up transformers. This first one steps the voltage up to 22,000 volts AC, and then we step up again to 500,000 volts AC. Remember, if I step the voltage up with the transformer, I increase the voltage, I step the voltage up, the current drops. So now I send out the power, high voltage, low current, and because I'm reducing the current, there's losses called I squared R losses. I squared R is, of course, power. So I squared R in a wire is usually considered a loss. So I squared R losses are reduced if I drop the current down. And that's what happens when I use the step-up transformer. So we step the voltage up, we transmit the energy, high voltage, low current, out over these long distance transmission lines. And those, again, the voltage is 500,000 volts. And then when we get close to the city, we're going to start to step the voltage down. So we step it down, we step it down. Here we step it down to 66,000 volts. These are short distance transmission lines. So these are not the telephone poles that you see on the street. That's a different type of structure. 66,000 volts. And then we step down from 66,000 to 4,800 volts through these step down transformers. You probably see some of these step down stations in your community, or you may have seen them in the community. Now we get to the level that you're used to. These are the normal telephone poles or utility poles where the voltage is stepped down, 4,800 volts, is stepped down to the voltage I discussed in class yesterday, 240 volts, two phase, and we can split the phases so I can get 120 volts and 240 to a residential customer. So when you get a chance, go back, read section 1 and 2 here, and it will give you a little bit more information. I think it's more concrete when you can actually see the picture. I mentioned the generator, a rotating machine, and I tried to describe this in the lecture. I don't know how good of a job I did, but I think this picture is clear. Here is a picture of the slip rings. These slip rings allow the coil to rotate in the magnetic field through 360 degrees and maintain electrical contact for the load without the wires getting twisted up. So you have these brushes that kind of ride against these rings. And you can imagine some springs forcing the brushes down against those slip rings to maintain contact. Notice I have the north-south magnet, magnetic flux, the permanent magnet, and then I have the coil that we went over yesterday. We talked about the two coils. I think I called one A and B, but you can see they show the current going one way in one and going the opposite way in the other, because of each one of these conductors is traveling a different way in the magnetic field. And using that right hand rule, you can determine which way the force on the electrons would be, and therefore you can determine the direction of the current. And speaking of right-hand rule, here is an example of what I was trying to show you in class. This is your right hand. Here is a charged particle. They use a plus charge as a test charge, but they have your right hand, and they say that, or they're showing you that if you put your fingers in the direction of, this is the magnetic field. Remember, B is for flux density, V is for velocity of charge or conductor, and M is the force on that conductor or charge. And so if I use this, if I orient my hand this way, my right hand, then you can see the force on the charge. So the charge is actually moving in the direction of V. The magnetic field, the north pole is here, the south pole is here, so the magnetic field is in the direction of these fingers, and so the force is actually perpendicular to the plane of V and B. So if this was a conductor, the charge would be pushed up. Now they're showing positive charge, so if positive charge is pushed up, the negative charge is pushed down, and it's a separation of charge. If I change this velocity vector, if I flip it over, then you can see what's going to happen to that force. Instead of going up, if I flip this over, then that force now is going to go down. The palm of my hand, if I take my thumb and I flip it over, the palm of my hand, that F vector is pointing down. And if I keep alternating that back and forth, you can see the push-pull effect that I was talking about to cause alternating current, the effect of alternating current, which is caused by an alternating voltage. Now, the other thing I was trying to show, and I don't know how good of a job I did, but I was trying to show you as this coil, let's go back to this picture, as this coil moves around 360 degrees through the magnetic field, it cuts the flux. You can see here, this is a cutaway. They're just showing the two conductors, conductor A and conductor B. So maybe let's say this is conductor A and this is conductor B. And they're just showing, you're looking at the side of the conductor. So that cross piece is like right here. Notice as this thing is rotating counterclockwise. Imagine the coil rotating counterclockwise. And here's that position 1 that I talked about in class. Right at position 1, as this thing starts to rotate counterclockwise, we're not cutting any flux. As this is rotating, conductor A is moving up, conductor B is moving down, but we're not cutting any flux. You don't cut flux if you move with the field. You only cut flux if you move across the field. So if I'm not cutting any flux, then there's no force on the charge. If there's no force on the charge, there's no separation of charge. If there's no separation of charge, there's no voltage. And if there's no voltage, there's no current. So at position 1, no voltage, no current. But notice as we start to move up, conductor A is here. I don't know if you can see it or not, but there's actually a dot here and an X there. This is showing the direction of current. Here current is coming out at you. The dot shows an arrow coming towards your eye. It's going across this crossbar, which is not shown here, and then going into conductor B. And notice at position 2, I'm cutting, here I wasn't cutting any flux, now I'm cutting more flux. So the force has increased now, which means the amount of charge that's separated has increased, so the voltage has increased, and therefore the current is increased. When I get up to 90 degrees, I'm cutting the maximum amount of flux on both conductors. They try to exaggerate the drawing here, so you can see here I'm actually cutting more flux lines right here. They're just showing a couple here, but I'm cutting the maximum amount of flux on conductor A and the maximum amount of flux on conductor B. So at this position, when the coil is at this position, we're cutting maximum flux, which means there's maximum force on charges in the conductor, which means there's maximum separation of charge, which causes maximum voltage, and therefore produces maximum current at 90 degrees. Now notice the dot here on A and the X here on B. Still the max current now is coming out of A going into B. So now we're going to continue our rotation in this second diagram down here. This is figure 13.4. Figure 13.5, notice now we switch position. Conductor A is now over here and conductor B is here, whereas before conductor A was here and B was here. So we went from this position all the way around to where conductor A is like right here, and conductor B has went to that position. So that's like a half of a turn. And so now what happens is, since the conductors have changed its position, the direction of the current in those conductors is going to change. But also notice that at position 4, conductor B this time is moving up, conductor A is moving down, so we're not cutting any flux until we start to get out of that position 4. As we move up, we're cutting more flux, which creates more current. And again, when conductor B is at 90 degrees, we got max current, max voltage, and max current. And we continue around. And what happens, and I tried to show this in the video, I'll review this again in lecture tomorrow. If you were to put an arrow on this conductor, if you put an arrow on it and watch it spin around and look at the projection of the shadow of that arrow, then what you would plot out, and what they're trying to show you, is this right here. Notice that arrow, that rotating arrow, we call it a phaser, and I'll say more about that when we get back to our lecture. But right here, that arrow is at 0 degrees. That represents the coil at position 1. And so the projection, if I shine a light on that, it's just a dot. 0 degrees, there's no force, there's no voltage, there's no current. As that angle right here starts to increase, so maybe we move from position 1 to position 2, you can see down here now, when that arrow is up at position 2, there's a projection. This represents the height of the shadow that would be right here. They're showing you at whatever it looks like 45 degrees, I get more projection, which means more, indicates more voltage and more current. But look at what happens at 90 degrees. At 90 degrees, the arrow and the shadow are maximum. So that shadow actually gives you an indication of the force acting inside of the conductor, which produces the voltage. So if I have maximum force, I got maximum voltage, which produces maximum current. And notice I have a maximum at 90 degrees, and that is position 3. And so if you trace this out, it keeps going around and showing you where the phaser is, the arrow. Now we're over here in quadrant 2, so that shadow is shrinking. And now we're back at 180 over here. So we moved from this position all the way over conductor A to that position where B is. We went half of a rotation. And you can see half of a rotation how the force is going to behave. And that voltage basically is going to follow the behavior of the force. When I'm back at 180, we're back at 0. It's at 0 because, again, at 180, we're not cutting any flux. Conductor A is now moving down and conductor B is moving up, but we're not cutting any flux. So if we continue around, all the way around 360 degrees, what you get is a force that acts like a sine wave. Therefore, the voltage produced by that force is going to be sinusoidal, and the current produced by that voltage, it too will be sinusoidal. So pay close attention to this graph when you guys look at that. This shows you, and I'll try to go back and I'll talk a little bit more about this and try to make it a little bit more clear, but I think this diagram shows a good picture. So you can look at that. So as this thing moves around, we'll talk about omega, the angular velocity. The angular velocity refers to the rate at which this coil is spinning around. So now this arrow that we attach to the coil, basically we can use that to kind of show us where the coil is, and we can talk about the arrow instead of the coil, just kind of abstract from the coil a little bit. And so the faster this arrow is turning, the higher the angular velocity. Angular velocity has units of radians per second. A velocity would be like miles per hour, meters per second. Angular velocity would be degrees per second, or more commonly, radians per second. So this is showing the angular velocity. How fast is that coil rotating in the magnetic field? At 100 radians per second. Here, they have one that's faster, 500 radians per second. And notice the sine wave produced. The more, since it's radians per second, I call it time space. This time right here, that time space, if it goes around in 1 second, in a time space of 1 second, it goes around 100 times. Well, if I take that same 1 second and go around faster, this goes around 500 times in a second. So I got to squeeze these humps together more. And again, I'll explain that when we get into the lecture next time, and I'll show you what I mean by time space and how this works. So read this and hopefully you can make sense out of it. So the higher the angular velocity, that is the faster the coil turns, the closer these are called cycles will be to each other. So hopefully that helped a little bit, make a little bit more concrete what I was trying to talk about in lecture, in the last lecture. Review this, and if you have questions, let me know, and I'll probably refer to this document so you kind of have a picture in mind. So you guys have a great rest of the day, and I'll see you next time. Thank you.